Hello guys, I welcome you back to Global Education Zone. And today in this episode, we are going to be dealing with electric field part 1. Now, when we talk about the electric field, I'm going to be using this video as a proper introduction because this electric field, we are going to be having 3 series of electric field. So, when we talk about electric field is the field that has to do with electricity, right? Now, electricity is something we cannot see, and this electricity, it's everywhere. It's just that we discovered it only recently. Electricity has always been existent since the beginning of the world, but it's only like around 100 years ago since till we learned to harness, apply, and direct this electricity, and that's why we have electrical devices today. So now in this series, we are going to be dealing with the electric field, and electric field is the part that we have to talk about before we can totally understand the concept of electricity. Now, I'll talk about the electric field. Electric field has to do with the region of space that is being influenced by an electric force, and this electric force, it's always felt and detected by instruments. But before we talk about those, let's talk about electricity itself. Now, electricity is a phenomenon that occurs when the electric field is moving around from one point to another. So basically, that is basically current electricity. So electricity is just a phenomenon. It is the result of an electric field, and this electric field, it is brought about by the existence of an electric force, and this electric force can only exist when there are charges. So charges are kind of like at the grassroots of understanding electric field, right? So basically, let's talk about the electric force first. The electric force between 2 point charges Q1 and Q2 separated by distance R is directly proportional to the product of the charges. So let's have that on the screen. So here we have that the electric force between 2 point charges Q1 and Q2 separated by distance R is directly proportional to the product of the charges and inversely proportional to the square of the distance between the charges. So in this case, we are talking about the fact that this electric force, just like I mentioned earlier, before it can exist, it needs charges. Now these charges, they are kind of like the elements that help us to understand electricity. Now these charges, they are not kind of like you cannot see a charge, right? But it's existing because it is the product of our imagination. Now this electricity is a phenomenon, but the scientists, they actually they modeled everything. What we understand things through models. These are models by which we understand the phenomenon of electricity and electric fields. You get it? So now we have a model, and this charge is a model. It's kind of like an ideal model. Reason for that is because when they discovered electricity, they discovered that these charges, there are some things that are entering and leaving some points in these conductors. So we're going to be talking about conductors though. Now these electric charges, they are the embodiment of electricity, right? And electric force can only exist between one or more charges. You get it? So now these electric force is between 2 point charges Q1 and Q2 separated by distance R. So and it is directly proportional. So what that means is that it increases to the same extent as the increase in magnitude of the charges, and it's directly proportional to the product of the charges and inversely proportional. That means it reduces with respect to the square of the distance between the charges. So that's basically what you need to understand in the electric field, and we'll be dealing with something else in this concept. And let's move on to the next concept, which will be on the force. Now this force, we are talking about this force now. This force has to do with the fact that the fact that it's an equation. It is a representation. It helps us to calculate all and help us to understand these charges more. So this force is basically it's called Coulomb's law, and it is the electric force between point charges, so which is F, and it's proportional to Q1 Q2 over R squared. So that's the magnitude of this force is given by F equals K Q1 Q2 over R squared, and in the above equation it's a constant of proportionality which is called K. So now this K, it is given as 1 over 4 pi E naught. Now this 1 over 4 pi E naught is a constant on itself, and it is known as the permittivity of free space. So basically this this E naught itself is the permittivity of free space, and that K is a constant. So and then when you calculate the value of K, most of the time it amounts to approximately 9 times 10 to the power of 9 Newton meter squared per Coulomb squared. So basically that is something we need to understand about this aspect. Now That was for that. Now I hope you understand the introduction to this electric field. So today in this episode we're going to talk about electric force, and you would learn how to calculate the electric force between 2 point charges. So that's exactly what you've done here. So with this equation, you can actually calculate anything you want to calculate. So once you know that force is proportional to the product of charges divided by the square of the distance between them. So you can, when you have any of these um, um, variables, you can always calculate the missing one. So as long as you have all but one variable, you can calculate and perform operations on this equation. So now you should also be able to explain electric field intensity and electric potential. So let's move on to something else. That would be on this, and I talked about this, that it's E naught is the permittivity of free space, right? So let's move on to something else. So this is an example now, and that's one of the aims of this video, to make you be able to calculate the force that exists between 2 point charges when given their distance and so on and so forth. So now in this case, we have in this question, we are asked to find the force of repulsion between two protons. So these protons, they are 1.6 times 10 to the power of 9 coulomb each if the distance between them is 5.3 times 10 to the power of 11 meter. So in this case, we are taking the constant k. So you remember that we agreed some slides ago that 1 over 4 pi E naught is the embodiment of the constant of this Coulomb's law. So this is Coulomb's law we are using here. So we have to calculate the force. So first of all, I need you to know that this force equals to 1 over 4 pi E naught multiplied by Q1 Q2 over R squared. So when you plug in your values, you know that Q1 and Q2, they are both 1.6 times 10 to the power minus 19. So if you had some basic knowledge on science, you should know that 1.6 times 10 to the power of minus 19 is basically the charge of an electron. So now when you plug that into the equations and the value of 1 over 4 pi E naught, you would get 8.2 times 10 to the power of minus 3 Newton. So as you recall, Newton is a unit of force. So this force, obviously, it's actually a small force, but when you accumulate the group action of different charges, because these charges, they are actually minute, they are very minute, and when you accumulate the effect of these forces, you realize that it is a very great force. That is why you can actually make use of electricity to um to um to drive a car. You can make use of electricity to make appliances work. So the reason for that, they can do work because of these forces that exist between charges. So you understand the concept now. So this is the basics of it all. So let's move on to something else in this video, and the next concept we'll be dealing with is I'll be giving a demonstration here. So this is a demonstration for you to understand. I need you to understand electric field intensity, and electric potential. So let's talk about electric field. Now, an electric field is a region of space, right, that is under the influence of an electric or electrical force. So basically, you can call it electric or electrical. So now, this electric field, it is kind of like a region of space. The reason is that we call it electric field because it is a region of space that we cannot we don't even know the bounds, you get it, but we can always be speculative by the reason of mathematical and analytic methods. So you can always estimate where the regions of space that this electric field is going to be existent. So basically, with that, with the essence of that, that is why we are able to understand that this arc represents the what is known as the electric line of force. So this is the line that is drawn through the charges. These dots here, they represent the charges. This the ends of these lines, they are the points. So these points A and point B, they are the points where the charges are existent. You guys. So now this electric field, it exists in a region of space, and this region of space can be mapped. So what you are seeing in this on the screen now is called an electric line of force. That's what is here below on the screen here. This is called an electric line of force. Now this electric line of force, it is actually the imaginary lines. So they are imaginary lines drawn in such a way that the direction at any point is the direction of a unit positive charge. So let's have the definition here. We'll have the definition now. So the strength of an electric field or electric field intensity at any point is defined as a force per unit positive charge or at that point. So basically, the strength of an electric field is the force per charge. So that is the strength of an electric field. So that means it is basically the amount of force that is represented per unit charge on in a region of space of an electric field. So now that was the definition I needed you to understand. Let's go back to this concept of electric line of force. Now this electric line of force, which we define them as a line, an imaginary line, right, that represents the path or direction of or region of an electric force. So now this is you can also call it. I'm giving an alternative definition now. The line of force is a path in which an isolated small positive charge would move if placed on its own in that field. You guys, so if you place an isolated small positive charge, so we are just assuming now. So in science we do a lot of assumption, so it's not actually possible to lift a charge. So I don't know how advanced science has gotten to now, but in personally I don't think it's actually possible to, but it might actually be possible in the near future. But you cannot kind of lift a charge and put it in the field, right? So but I don't know whether that is possible. If you are aware of that, you can challenge me in the comment section of this video. I want to hear your challenge. Now basically we are assuming that we can lift a unit small and isolated positive charge, and then when we place it in that field, the direction of that positive charge is going to give us the electric line of force at a particular point. So in this case, in this diagram, you can see on this screen you have an arc, right? So at this point P, you can see an arrow that is showing the direction of that unit positive charge. That is the direction it would move if it was placed in the field. Now those of you who have analytical mind, you would understand that this is an arc, and this at that point P, that direction is representing a tangent. So that means the direction of a unit positive charge is tangential to the arc, to the electric line of force. So I hope you understand that concept. So the reason why we are falling back to mathematics is because physics and mathematics, they are kind of intimate. They are quite tied together. You get it? So let's move back to this concept of the strength of an electric field. So now the strength of an electric field, or electric field intensity at a point, is the force per unit positive charge. So that means, what that means is that is the force that is being exerted on or by a unit positive charge. Now this force exists because of this charge. You understand it? That's why when I say on or by a unit positive charge, that is, the force can be exerted by that charge or by another charge that is mutually dependent on that initial charge. You get it? So this force exists as a result of interaction between these electric charges. So if it were only one charge, then we would not need any mutual interaction, and there won't be strength of an electric field. So but this strength of an electric field is, it's a mutual phenomenon. It's an effect that is caused by the mutual interaction of charges, and depending on the magnitude of those charges, you can have those strength of electric field. It is known as the electric field intensity. Now let me explain this in a better way. Now just like when you have a glass of orange juice. Now some orange juice, they are made by pure orange, while others are diluted with water and sweeteners are added. So basically, when you have a pure orange juice, you notice that it's actually quite thick. So basically, that's how I want you to understand the strength of an electric field. So these charges are like juice. So those of you in America, you call it juice, right? The juice, that's what you call electricity. Basically, it's kind of like a slang, I guess. So now this juice, it's kind of thick. So that orange juice is kind of concentrated. So I want you to see the strength of an electric field as a concentration. So the thicker it is, the more the concentration. That is, the more the charges are clumped together. So that is the force per charge. So if you have a region of space where there are a lot of charges in a particular region, so that means the force per unit charge is going to be great. You got it? So then, but if you have a region where these charges are actually sparse, it won't be as strong as the first scenario. So moving on, let's move on to another concept. So I hope you understand that concept of electric field intensity and electric line of force. Now let's talk about a question. Yeah, we have a question here, and we are to attempt the question. So we are told that two parallel plates are charged at a voltage of 40 volts. If they are separated by a distance of 10 centimeters, calculate the electric intensity between them. So in this case, we have our formula as the intensity of an electric field is basically the force per the charge. So it's also defined as the potential difference per the distance. So that's another way of defining it. They are both the same thing. You get, they still give us the same thing. So if you have a potential of 40 volts and you have a distance of 10 centimeters, you just plug in your values in the equation, and then you have that 40 divided by 0.1 meter. Because when you convert 10 centimeters to meters, you are effectively dividing by 100, right? So you get 40 divided by 0.1, and that's 400 volts per meter. So that is the strength of this particular electric field. So I hope you understand the concept. Now let's move on. So we have the concept of we have another concept which we'll be talking about in this video, and that's the concept of these capacitors and all the rest. So now basically we have these capacitors, and these capacitors, they are associated with electricity because they are useful in regulating the behavior of electric forces. And let's talk about the nature of capacitors. So these capacitors, their function is basically to store electrical charges. So I'm hoping in the near future I'll be able to make a series on electricity, and because I'm kind of interested and intrigued by electricity, so I like talking about it. So hopefully we'll be able to talk about it in more detail in the subsequent um, episode, and hopefully in the near future I'll make an episode or a series on electronics. So basically the working of electronics, you have all these electrical devices and all the rest. So hopefully I'll be able to make a series on that. But today let's talk about the basics of electricity. Let's do the fundamentals. So now talking about the capacitor. So these capacitors, they are used to store charges, and basically the capacitance of a capacitor is basically defined as the ratio of the charge on either plate of the capacitor. So in a capacitor you have what is known as plates. So these plates, they are placed parallel to each other, and there's a distance between them. So the capacitance of a capacitor is the ratio of the charge on either plate to the potential difference between them. So that is basically charge divided by potential difference, or voltage. That's charge over voltage. That's called the capacitance of a capacitor. So obviously in anytime you have an equation, the numerator is always directly proportional to the left hand side of the subject, and then the denominator is always inversely proportional. So when we say directly proportional, that means that the capacitance will increase with the numerator and it will decrease with respect to the denominator. So when you have a capacitor, you have a very large potential difference. That means the capacitance is low. When you have a large charge, that means the capacitance is high. So the reason for that is that actually in a capacitor, the capacitance is determined by the ability of that capacitor to store charges. You get it? So now that means that this capacitor, in a very good capacitor, it will be able to store a very large amount of charge. So, and because that is the essence of a capacitor, to store charges, right? But then when you have a very large potential difference, it kind of reduces the effect of the capacitor. So when you have a large potential difference, you will need a very large amount of charge to keep up with that. So that's to make everything constant. So now this diagram we have of the capacitor here, we have the symbolic representation, and then we have the pictorial view. So in this pictorial view, I want you to notice the metal plates. These plates are metallic because they are conductors. So for you to be able to store charges, you need a metal that can accept and store those charges. Not as if insulators cannot also store charges, but they cannot. They are poor. They are very poor at transmitting charges. So insulators, they don't transmit charges easily because their atoms do not have free electrons to transmit charges. So basically, that's why you don't use a insulator, I assume. But in some cases, you can have ceramics around these metals to insulate them and to store the charges better. So this dielectric is basically going to be that ceramic. So that dielectric, it can be made of any material. That dielectric is an insulator. It is not a complete insulator because it has a kind of dielectric property, but it's useful to store the charges between those metal plates. So these metal plates, they are the major things we're talking about. So, but actually, we also need to talk about the electric rather. We also need to talk about it because it also depends. It also determines the strength of that capacitor. Now, this capacitor, which we've been discussing about, is there are different arrangements of the capacitor that can help us to in calculation. So in physics, when we talk about physics, at the end of the day, we will often fall back on mathematics to give us some analytic explanation of what we're talking about. So basically, physics is theoretical, I know, but it's also very analytic. You need to have a very analytic mind to completely understand and digest physics. So that's why we come to the calculation involved, and we have in series the capacitor is arranged in series in the first diagram, and then the second diagram they are arranged in parallel. So there are different um, formulas for calculating the effective capacitance. When we talk about effective capacitance, it is basically the combined action of capacitors in a circuit. So in this first diagram, we have a series diagram, and then they have their combined effect, and that is basically the sum of their reciprocals. So basically, the reciprocal of the effective capacitance is equal to the sum of the reciprocals of the individual capacitors. Then the second case, in parallel combination, we have the is simply equal to effective capacitance is simply equal to the sum of the capacitance. So that is mathematically represented by equations 1 over c equals 1 over c1 plus 1 over c2 plus 1 over c3. That's a series, but in parallel we have C equals C1 plus C2 plus C3, so on and so forth, depending on the number of capacitors you have. But then let's talk about the work done in charging the capacitor. And basically that means in electricity we basically move charges around, right? So and that moving of charges around, it dissipates energy, right? So this dissipation of energy, some of it is captured by the capacitor. So and that is called the work done in charging the capacitor, because when you charge the capacitor, you are actually capturing work and then you are using it to charge the capacitor, right? So now the energy stored in that capacitor is as a result of the work done in charging the capacitor, and it is represented by W equals to 1/2 QV. So you recall that Q represents the charge between the plates of the capacitor. Then you have your V, which represents the potential differences between the metallic plates of that capacitor, and then you have your C, which is capacitance. So your work done, which is W, is represented by this equation. But my favorite here is half CV squared. So basically, it is actually quite easy to understand, because it's easier to calculate capacitance and potential difference. So, but if W is in joules, you have Q, which is charge in coulombs, and voltage is the unit of V. Then we have farad as unit of C. So I hope you understand that concept. And finally, today we are going to be dealing with the questions. And in this case, the questions here, we have the plate of a parallel plate capacitor 5.0 times 10 raised to the power of minus 3, right? That should be minus 3. So the plate of a parallel plate capacitor 5.0 times 10 raised to the power of minus 3 meter apart are maintained at a potential of 5.0 times 10 raised to the power 4 volts. So we have to calculate the magnitude of the electric field intensity, the force, and the acceleration on the electron. So now basically these are questions for you to attempt, because this is the end. We have come to the end of this video, and these are questions for you to attempt. So you can just try the questions and let me know in the comment section your answer. So I hope you enjoyed this video. Thanks for watching.